Okay, so in this video, I'm going to quickly go over the structure of units within PhysLean. So I'm using my iPad here because my Mac ran out of charge. So I'm on the GitHub app. I'm going to go into code. I'm going to go into PhysLean. And these are the main directories of PhysLean. And I'm going to go into units. So within any file within PhysLean, the main directory or the main file is going to be this basic.lean one, this one here. So I'm going to click on that. And we can see the doc string. So this first bit's the module doc string, and it tells us everything that's in this file and all of the key results. But let me go through this individually. So this type here, this dimension type, is the type that is going to keep track of the dimensions of objects or terms of specific types. So in our case, the dimension has a component, which is the length dimension, the time dimension, the mass dimension, the charge dimension, and the temperature dimension, and they can all be rational numbers. So this next bit here, this namespace within dimension, all the way down to here is basically just proving some nice results about dimension. So, for example, that it forms a commutative group that you can multiply two dimensions. In other words, a multiply here really means you add the individual components of the dimension. There is a zero dimension, and so on and so forth. There's an inversion dimension, which is basically the negation of a dimension. So if something has dimension time, the inverse of that is negative time. And we define these shorthands for given dimensions. This shorthand here for the length dimension, this shorthand here for the time dimension, and these shorthands for mass, charge, and temperature. So that covers dimensions, and again, dimensions really is the notion of this thing has a dimension of time, this thing has a dimension of length, or if it's like a speed, this has dimension time times by length inversed, and that's covered by this dimension type. So let me go down to now unit choice. So the approach that we're taking in PhysLean is that things are going to be connected to the actual definition of, or rather units and dimensions are going to be connected to the actual choices that they correspond to in physics. And I should say that the implementation of units here may change in the future, and dimensions may change in the future. I'm just giving you an overview of what is currently in PhysLean, so you'll kind of have an understanding of what's currently there. So this units choice thing is the thing that is gonna tell you what choice of units that you are using. So it is a structure. So a term of this type corresponds to a choice of a length unit, a choice of a time unit, a choice of a mass unit, a charge unit, and a temperature unit. So an object is dimensionful if it kind of depends on such a choice of units in a given way, and we'll get onto that in a second. One of the key definitions here that depends on the unit choice is this thing called dim scale, and this basically says that if you have two unit choices, u1 and u2, and a dimension d, this is a real positive number which corresponds to this thing here. And what this is saying is that if you change from units specified by u1 and go to the unit specified by u2, and you're working with a quantity of dimension d, this is the factor, this is the scaling that you would expect. So for example, if d here just corresponds to length, all of these terms except the first one would be 0. And if u1, for example, if the length component was miles and the second one was meters, this would be the conversion of a quantity from miles to meters. Or this is the scale factor that you need to multiply a quantity when you're converting from miles to meters. And there's a bunch of properties of this dim scale. Maybe you can think of some more properties that you have of this, and if you do, feel free to add them to the project. So scroll down a bit. Within unit choice, you can also define specific instances of units. So One instance of a unit choice is, of course, the SI units, where, for example, length is meters, time is in seconds, mass in kilograms, charges in coulombs, and temperatures in kelvins. And again, we can prove a bunch of properties related to those choice of units. So the way that types are going to carry dimensions within PhysLean, or the way that they currently carry dimensions within PhysLean, is this class carries dimension. So what does this say? This says we have a type M, and we're going to assume that terms of type M carry a dimension, and that dimension is going to be specified by this term of the class. So for example, if we assign to M this instance with a dimension of length, then we're saying every term of type M should be assumed to have this dimension, or to carry this dimension length. We also have this module carries dimension, and really this is the same as carries dimension, except modules carry dimension just behaves a bit more nicely. It prevents what's called a typecasting diamond, and it basically works more nicely with modules. So if you're defining a dimension on a module, you should use module carries dimension. Otherwise, you should just use carries dimension. So one of the key things about PhysLean and its use of units and dimensions is that the notion of a dimension, or having a dimension, is a property, not a structure. So we're not defining types and we're saying they have this dimension. We're proving that they have this dimension. And this statement, or the proposition that needs to be proved, is this one here. So this says that if you have a term in M that actually depends on a choice of units, then that term has the dimension F, or has the correct dimension, has the dimension of M, if under a change of units from U1 to U2, it scales by this dimensional factor. And this is kind of what we would expect. If you're changing a quantity of dimension length, for example, is going to change by a scaling that depends on that dimension. And this unit scale, this dimension scale, is really that scaling. This dimensionful type is basically the type of all such maps from units choices to M that has this property that it has this dimension. So it's basically every element of M that carries a dimension. And we'll see in a second, let me scroll down a bit, that there is an equivalence between M and dimensionful M. Basically, every object in M can be made into a map from units choices to M, given a choice of unit, and there is an inversion map to this. And this basically says you really can think of this M and this dimension for M as dimensional for M, where you have chosen a specific unit. And this is basically, this equivalence is basically due to the fact that you are just multiplying, when changing the unit for a quantity in dimensional for M, you are just multiplying by a scalar. So in addition to something that carries dimension, a type that carries dimension, for example, time, we have this unit dependent thing. And this says that the type M doesn't necessarily carry a dimension, but it depends on a dimension. So, or it depends on a unit rather. So, for example, a measure may have a unit dependence. For example, the thing that you integrate over, it depends on the choice of units, but it doesn't really make sense to assign that a given dimension. So this is where unit dependent comes in, and this is really used to define things like functions from one type of a dimension to another type of a dimension. And we'll see in a second how this is used to define the notion of being dimensionally correct. But basically, the basic class or field of this class is this scale unit, and it basically tells you how you should change this quantity M on a change of units. So if you go from this unit to this unit, this argument of unit rather to this argument of unit, given this M, then you get a new M, and that has to satisfy certain properties which are basically related to transitivity and the identity. We then define some other classes which are very much related to this unit dependent class, but behave nicely with respect to things already defined, such as the multiplicative action on M, a module structure on M, and so on and so forth. So there are a bunch of properties related to this, which I am going to skip over. and all part of building an API to make units as user-friendly as possible, but of course there can be lots of improvements to this. And here we're defining, so in this code here, we're defining a bunch of instances of this unit dependence. So let me try and find the most basic one. So basically, if you have a function if you have M1 and M2 and they're both unit dependent, and M2 is unit dependent, then the function from M1 to M2 is unit dependent, and the scale unit is basically you scale the target after you've applied the map. And you can define variations of this, and you can define them for linear maps, continuous linear maps, and you can define them for things like meshes as well. So the key result, the key definition of all of this is dimensionally invariant. And what this says is that if you have a quantity m, a term m of type m, and m is unit dependent, then on scaling m by u1 and u2, you get back m. And why is this equation important? Because propositions that depend on arguments which depend on which carry dimensions or are unit dependent is unit dependent. And this proposition here is the statement that proposition or that function is dimensionally correct. So this is dimensionally invariant. It's really the proposition that if this is true, then your proposition is dimensionally correct. And this is something that you have to prove, and you get from that a bunch of theorems that you can use to make statements about theorems or propositions with different units. So we're not just tracking dimensions here, we're proving things have dimensions, and that gives us a lot more versatility. That said, you can define certain classes like this demul thing, which allow you to more efficiently track dimensions. And that can allow you to better prove that certain things that satisfy this property here. So these sorts of things you can define to track dimensions to make sure you can't multiply things of different dimensions or divide two things of different dimensions within PhysLean are basically can be there to help you prove stuff about this is dimensionally invariant. And these sorts of structures can be improved. So I'm going to skip the rest of this file because it's not so important and go on to things like the derivative file. So in this file, it's really simple. We proved that the derivative, or this f derivative in PhysLean, is dimensionally invariant. In other words, it obeys dimensions in the correct way, in the way that you'd expect it to. And it says that if you take a function from m1 and m2, and m1 and m2 both carry a dimension, and the f is dimensionally valid, and it's differentiable, then its derivative is dimensionally valid. And this is what we'd expect from the notion of derivative carrying certain dimensions. And we can do the same with integrals. In this file, you can put a class of, a class or an instance of meshes, for integral meshes carrying a dependence, a unit dependence. And we can prove here that integrals are dimensionally invariant. In other words, they behave nicely with respect to dimensions. This file contains examples. So you can, for example, define 400 meters as a dimension for quantity. Oh, actually, sorry, let me go over to this with dimension file before that. So with dimension is basically a type M which carries an instance of dimension D. So it's basically saying we want the type M, which currently doesn't carry any instances. We want to give it a dimension D, and we want to create, a new type where the values are in M, but the terms of that are expected to carry a dimension D. And this is basically what this structure here is. And the relevant instance is this one here. Sorry. The relevant instance is this one here. So this is basically exactly the same as M, except it carries this additional instance here, that it carries a dimension. And this is typical of the sorts of things that you'd see in MathLib, where you may not want to put an instance on a given type, so you do with like LP, which has a different type of norm, for example, or a different type of inner product. So yeah, and then this examples file basically contains a bunch of Examples is again is improving, and it probably, if you're watching this video at a much later date to when I make it, it will have been improved of different examples of different quantities. So hopefully that has given you an overview of units in PhysLean. And like I said, this is very much possible to change in the future. And if it does change, that's great, because it's going to get better. But this is what is currently out now, and this is at least one way to implement units and dimensions within Lean. So yeah, thanks for watching. Hope that's been informative.